Okay, before we go to the derive the plane element stiffness, okay, we have to understand the theory of elasticity first. Okay, this is just only the introduction for theory of elasticity. So then, if you you may have to review it again from the mechanics of material textbook or the advanced mechanics of material or theory of elasticity again, if you would like to understand more detail on this equation. Okay, but for now we may just overview and we will apply this equation to the plane problem that we will apply to. Okay, so then if we consider the differential equation for the straight at any point, okay, this is we will consider the straight at a point also, but we will consider the plane xy plane first. For the xy plane, we may have the state of straight that is acting along the surface. This is the surface x plus bx. This is surface x plus bx. Okay, this is maybe the surface x. Okay, in the same manner for this is the plane y. Okay, this is a plane y plus by for that case. Okay, but actually this is the straight at the point. Okay, that is as I mentioned that we have the body, right, and we have the applied force to any point, but we will focus on just only this point. Okay, we zoom out, and then we consider just only the plane xy. Okay, so for the summation of force along the x direction, we have the equilibrium equation like this. Okay, in the same manner for y direction. Okay, if we consider just only two-dimensional problem, we may have the equilibrium equation like this. This is the summation fx equal to 0, and this is summation fy equal to 0. This is actually it comes from the free body diagram of the figure C1. Okay, we have these two equations, and also if we consider the summation moment, that is it should be in equilibrium, it should be 0 also. We obtain the symmetry condition, that is tau xy equal to tau yx. Okay, that is for some notation. This is maybe the notation in finite element is maybe used sigma infinity, sigma xy and sigma yx. But for the text of mechanics of material, may have used the tau xy, tau yx to represent the shear. Okay, and sigma x and sigma y represent the normal stress. Okay, so then this is a stress tensor that we familiar with. Now we will use the notation that is sigma x become the normal stress, and tau xy, tau yx, tau xy, tau xc, and tau yc become the shear stress. So for this case, we may write the stress tensor like this: sigma x, sigma y, sigma c. This is tau xy, tau xc, and tau yc. Okay, and this is symmetry. Okay, this is stress tensor for this notation. So then if we consider the equilibrium equation in 3-dimensional, we will expand like this. Okay, we have 6 equations for 3-dimensional problem. Okay, and then we will consider the strain displacement relation and compatibility equation. If we consider the plate that has the deform, that is deformed like this. This is the undeformed shape. The dashed line is the undeformed shape. You see that the angle is become 90 degrees for each side. Okay, But when it's subject to the force, it may have the deformation like this, like the solid line, okay, the dark solid line. And we define the deformation. That is the length is changed from the x. This is the x is the undeformed. Is changed to be the x plus an increment of deformation, that is partial u by partial x dx. Okay, this is the deformation along the x direction. In the same manner, in y, if we consider in y direction, it's become dy partial v by partial y dy. That is for the sense of y. Okay, and also it has just not only the deform in axial only, it's deformed in another direction also. So it means that we have the change in angle, that is for this case the point A is moving the shape of the line AB change to be A palm B palm. It has an increment in y in y direction with respect to x also. Then we define this statement become partial v by partial x dx. Okay. Okay. And also for the case of actually, I think the picture from the text maybe how a little bit not correct for this case, for this line. Actually, it should be just only this. Okay, but for the text, it's maybe would like to show out. Actually, it should be just only this. Okay, it changed form. I may redraw. This is a deformed shape. Okay, and this is the undeformed shape. Okay, we have this angle, that is we define this length is partial v by partial x dx. Okay, and we define this like partial u by partial y dy. All right. Okay, so then if we consider the axial stress first, axial strain, sorry. For the axial strain, it means that we consider the length, the new length, that is A palm B palm minus AB divided by AB. That is the original length. But AB is become the x. Okay. So then let's consider A palm B palm. What is that? A palm B palm is defined by the length, the new length. The new length, that is dx plus partial u by partial x dx. Okay. Plus what? Plus this. As I told you that the figure here is maybe not correct. Okay. So you will see, I zoom out. This is A palm, this is B palm. Okay. This is dx plus partial u by partial x dx. Okay. This is partial v by partial x dx. Okay. So then we can find A palm B palm by this equation according to the Pythagoras theorem. You see that actually this form, okay, if we consider the strain and divide it by this full form, okay, we may call it the last strain condition, because when we would like to find A palm B palm, we have to take the square root of this term, right? That is, the square root term is induced at the highly nonlinear term. Okay, so then if we take care of this, so it means that we will solve for the last strain condition. But for this case, that we will focus to it is limit to the small strain for the small strain condition. For the small strain condition, it means that we will not consider this the higher order term. The higher order term that is maybe included in this term. Okay. So the higher order term is include of this term square, and also when we if you consider this term is maybe like the x square, right, plus 2dx partial u by partial x dx, okay, plus partial u by partial x dx square, okay, plus, okay, partial v by partial x dx square, and then after you take square root or something, okay. So we will see that we may consider just only the term that we focus on. After we linearize, we can simplify a prime b prime to be just only this term for the linear case when we use the binomial expansion. After we take the square root, okay, this is the highly nonlinear. But when we take the binomial expansion theorem, okay, so the higher order term will be reduced, okay, and we will include just only this. It means that for small displacement, a prime b prime is approximate to be dx plus partial u partial x dx, and then when we focus on axial strain, that is a prime b prime minus ab divided by ab. So it become like this, become just only this term. Okay, so then now we have the definition of epsilon x, that is become partial u by partial x. And for epsilon y, it's become partial v by partial y. Okay, this is I give you the binomial expansion also. That is you may if you would like to derive this, you may do it by yourself. That is from this term y it comes this term by using the binomial expansion. Okay, so then we consider the normal stress already, that is epsilon x and epsilon y. Let's consider the shear strain. Shear strain actually is the change in angle. The physical meaning is the change in angle. You see from this, if you consider this picture again, okay, this picture again, you see that the original angle of the shape is 90 degrees, right? It's a 90 degree. But if the shape is deformed, okay, we change from the red one to be the blue one. Okay, so then we have the change in y direction and in x direction like this term. Okay, and we may define this like the angle theta. For the small displacement, this is the theta 1, this is maybe theta 2. Okay. For small displacement, the increment in this direction, in y direction with respect to x, represent theta 1. Okay. And the increment in x direction with respect to y, we represent theta 2. Okay. So then if we combine together theta 1 plus theta 2, it is the angle that is changed from the original shape, that is changed from 90 degree. Okay, it's changed from 90 degree. What does it mean? It means that the first angle, the original angle, that's I will define. Original one. This is original one. Alpha is 90 degree. This is original one. After it changed to be this, it's changed to be alpha 2, right? This alpha 1. Okay. So this is alpha 1. Sorry, alpha 2. So then, if we consider the shape that is changed from 90 degrees to be alpha 2, so then we have alpha 1 minus alpha 2 is equal to theta 1 plus theta 2, right? Okay. So then this is the defined as the change in angle, that the change from 90 degrees to alpha 2. Okay, are you all right? That is the definition of shear strain. It is a change in angle. Okay, it is change in angle. Okay, we define like this. For the small displacement, gamma xy is defined like partial u by partial y plus partial v by partial x. And we have to concern about the compatibility condition also. As you will see that in finite element, we assume the displacement rate, and the displacement should be continuous and compatible for each point. So then for that case, we have to consider the strain compatibility condition. That for the plane problem, this condition will satisfy if the displacement satisfy this condition. So then it means that the strain is compatibility for any point for the plane problem. And you will see that from the text. That's the text of Logan. That's I copy this part of the text, that is the appendix C. This is the overview of the theory of elasticity. Okay, for more detail, you may have to consider the text of Boresi, that is the advanced magnetic material instead, in order to understand more detail for the theory of elasticity, that is the strain compatible. This is the equation for small displacement theory, that is composed of epsilon xx, epsilon yy, epsilon cc. Okay, this is the axial strain. Okay, and these are shear strain. Okay, that is actually is represent change in angle. Epsilon xy is equal to a half partial v by partial x plus partial u partial y. You see that it is a notation that epsilon xy is equal to gamma xy over 2. That's gamma xy we already defined with the shear strain. Gamma xy equal to partial u partial c plus partial w by partial x. But if we write in strain tensor, it's equal to epsilon xy. Epsilon xy, sorry, it's at gamma xc, right? It should be epsilon xc. Epsilon xc is become gamma xc over 2. This become partial u by partial c plus partial w by partial x over 2. And these are strain compatibility condition for three-dimensional problem. Okay, for three-dimensional problem, we have to satisfy all this. There is 6 equations. Okay, but just only for plane problem, we have to satisfy just only 1 equation. So then we have the strain displacement already. Okay, then we will consider the stress-strain relationship. For stress-strain relationship, for this case, we obey the elastic material. We obey Hooke's law. Okay, as you already know that for elastic material, the stress is related to the one constant that we call Young modulus. Okay, but in three-dimensional, not only the deformation from axial is for the outplane, we have the Poisson effect also. So what does it mean? It means that the axial strain epsilon x is composed of 3 components. It's composed of axial stress, the term of axial stress in x direction itself, and also axial stress in y and in z direction through the Poisson effect, okay, by Poisson ratio. So then epsilon x for 3-dimensional, okay, it is not just only sigma x over e anymore, okay, like 1-dimensional problem that we have solved for lot problem, for bar problem, for frame problem, and for beam problem. You see that we already define epsilon x equal to sigma x over e, just only this, because it is a 1-dimensional problem. But for in 2-dimensional and 3-dimensional, we have to include the Poisson effect also. Okay, that's why we have the strain and stress relation like this equation. It's composed of 3 equations like this. And we can rearrange this equation. We can rearrange this equation in terms of sigma x, sigma y, and sigma c as a function of epsilon x, epsilon y, epsilon c instead. So from this equation, from the above equation, we rearrange into this equation instead. So then you will see that for this case, as I mentioned it before, for 1-dimensional, you will see that you have the straight vector, just only one component, means sigma x, and you have the metric E, that is the elastic modulus itself. It's just only one component also related to the strain vector, that is just only one component, epsilon x. So you see that for previous chapter that we focus on 1-dimensional problem, this metric is 1 by 1 only. But for this case, if we write it in the metric form, okay, we will have this term. Okay, that is what does it mean? It means that the straight component, okay, for 3-dimensional problem is composed of 6 components, okay, related to the metric E. That is for 1-dimensional is just only 1 by 1, but now it's become 6 by 6, okay, and strain component is not only 1 component anymore, it's become 6 by 1 also. It's composed of 6 components. Okay, this is just in 3-dimensional. So then that's why to the plane problem and solid problem, it is not convenient to use the direct stiffness method to derive the element stiffness. We may have to apply the energy method, energy approach instead, in order to derive the element stiffness. Okay. So it means that for this case, if we define like this, okay, so the text not use E, it use D, okay, the metric constant, okay. So the metric constant for this case is called metric D. That's for 3-dimensional is equal to 6 by 6 component. It's defined by this metric, okay. So that is the overview of the 3-dimensional problem. Okay, because the limit of time, I think we may continue this topic next week. But I would like to mention to the class activity today a little bit before we stop the class. Okay,